You have started, Crispin? Okay. Yeah. Hello and good afternoon. The Public Outreach and Education Committee of the Astronomical Society of India welcomes you to the discussion series, Ask an Astronomer. I am Sarita Vig, and joining me in organization is Professor Aniket Sule from ASI POEC. Dr. Crispin Karthik, who is an associate member of ASI POEC, is helping with the streaming. Our eminent astronomer for today is Dr. Shashikiran Ganesh from the Physical Research Laboratory, that is PRL, in Ahmedabad. And the theme for discussion is Comets, the Majestic Visitors. Dr. Shashikiran will be giving a short presentation, which will be followed by a discussion. I invite our participants and viewers to note down their questions in the chat box. I will first introduce our speaker. Dr. Shashikiran is a scientist in the Astronomy and Astrophysics Division of Physical Research Laboratory, Ahmedabad. He joined PRL in 1995, and after his master's in physics from Gujarat University, he completed his PhD at PRL on the multiwavelength studies of Milky Way galaxy. His interests also include the minor bodies of the solar system. He is interested in astronomical instrumentation and is the principal investigator for the development of a multifunctional near-infrared instrument for PRL's upcoming 2.5-meter telescope. May I now request Dr. Shashikiran to kindly begin his presentation.
Thank you, Sarita, for the introduction and, in fact, indeed for the invitation to speak in this series. It's a pleasure to be here and an honor. So I will start with sharing my screen in just a moment. Yes. Okay. So is it visible now? I think my screen.
Yes, it is visible.
Okay, thanks. So, as Sarita has mentioned, my interest started when I joined PRL, I started working on comets. And in fact, Within the 1 year of my joining there was this spectacular comet called Comet Hadley, and which you can see here at sunset. This is a 2-minute exposure on film, and because in those days we did not have portable digital cameras the way we have in mobiles now. And you can see that even while the sun was setting, we could actually see the comet extremely well, and also some of the brighter stars. So what are these comets, and what do we do about studying them? So those are some of the aspects that I shall cover in this discussion. I hope that I will be keeping it at a very general level, and then if there are more technical questions, we can take them up in the discussion. So some of the slides might seem technical, so you can just ignore them and focus on the interesting aspects. Okay, so but right before this 1995-01, there was another comet which was quite a lot in the news. In fact, typically comets are usually orbiting the sun, but there was one comet which was discovered by the Shoemaker couple along with David Levy in 1993, and they found that it was actually orbiting Jupiter. Okay, and in fact, when they found it, when they observed it, it was pretty oddly shaped, and so they looked at it with HST, and this is the image with the HST. And they found that in 1992, it had in fact passed very close to Jupiter, and that's how it had split up, okay, into 21 fragments. And in the next year or so, it in fact approached so close to Jupiter that there was no way to escape. Okay, so then it crashed into the atmosphere, and the effects were seen for several years. And in fact, even I was able to see them with a small homemade telescope, with an 8-inch telescope, which I built during my college days. And I just show this here just to show that even with the kind of limited resources we had during those days, things were possible. And it was very thrilling to see these spots on Jupiter with a telescope that you have built yourself. Okay, so just wanted to bring that out. So, but going back further into history, what exactly do we know about comets, and what has been the kind of historical approach to this? So, comets were considered almost across all cultures as omens and signs foretelling floods or the death of kings and such kind of devastations and things like that. Aristotle was one of the first to start thinking of these as natural phenomena, but he thought that they were mostly atmospheric phenomena. So there, of course, the problem arose, and then he could not explain everything. Later on, of course, there were a lot of other observations, and there are a lot of historical records. Edmund Halley, for example, looked at the orbits, and using the recently proposed theory by Newton, he looked at the orbits of 1531 and so on, and decided that they were the same object, and predicted that they would again reappear in the 1700s. And this, of course, he did not live long enough to actually see it. So it remains that 1P Halley is the only comet to be named after a pure theoretician. Okay, although at that time I think there was no distinction between these branches. The earliest record of Halley could be the ones from 466 BC in the skies over Greece. More reliable ones are from the Chinese Han Dynasty, where they record it as a broom star, so a star with a kind of tail. And that is in fact the origin of the word comet, which in Greek means hairy object, okay, hairy star. And there were many other records in between. And the most famous occurrence in history is the Bayeux tapestry, and which actually depicts what appears to be Halley's comet. And in fact, you can see a group of people here looking up at the comet with awe and bewilderment, whether it is foretelling the death of their king, Harold of UK. For those who are interested further, you can join and look into this link here. In fact, again, Comet Hadley was in the news for all the wrong reasons in 1910, because there was a prediction that the Earth would be passing through the tail of the comet, and by that time, spectroscopic observations had been done of comets, and it was known that CN was one of the components, and so there were people who were, willing to take the money for all these reasons, and then they sold a lot of masks and filters and things which would prevent CN from poisoning you. In fact, even as late as in 95, there was this cult of people who believed that Hale-Bopp comet had an alien spacecraft in the tail, and that by committing suicide, they would actually be able to join that group. So there has been a lot of inaccuracies and a lot of omens and things associated with it. But what exactly are these? Okay, so before that, something about what Indian depictions are. Actually, I'm not particularly an expert in this, and I would just refer to you to Kapoor's work, where he has a lot of entries on his ResearchGate link. And for example, there is this Comet Current Science article by him about Comet Bapu Bok Newkirk, with the title "The Only Comet with an Indian's Name to It," which of course refers to well-known Professor Vainu Bapu. And in fact, when Professor Bapu discovered it, he had just joined the Harvard Observatory, and apparently it was just the first night of his observation. So that's something fantastic that one can think of. So going further, what are comets? So I should be brief, and so I will not go into too much of detail because I expect that most of you are familiar with what these are. So they're typically made up of rock and ice, so-called dirty snowball hypothesis. And they are orbiting the sun, spending most of their time away from the sun and in the far reaches of the solar system, typically a few kilometers in size. And the comet's tail forms when it comes close enough to the sun. It may pass, so in terms of comets of different types, they may be periodic visitors or they may be short one-time visitors also. So most of this I have already covered, but so every comet has a different and unpredictable behavior. So it's important to study each one for its own sake. But in the general picture, what we have found is that cometary spectra are very similar, especially when you look at the mid-infrared spectra. They're very similar to the young stellar objects and protoplanetary disks. So these are ideal objects to understand the formation evolution of the solar system. Essentially, they're the leftover material from the time of formation. So if we look at the classification and the reservoirs, then comet classification can happen in terms of the period of the comet, which means that you divide them into periodic comets wherein you have records for repeat observations within 200 years, and long period comets where orbital period is greater than 200 years. Okay, and same way in terms of spatial distribution, if you see, then you have the Jupiter family comets wherein the aphelia are just beyond the orbit of Jupiter, and these have relatively short periods of up to 6 to 7 years. Comets from the Kuiper belt come from the trans-Neptunian region and are still confined a little bit to the ecliptic disk. The Jupiter family comets are quite close to the ecliptic disk, the Kuiper belt a little more beyond that. So you can have inclinations of up to 30-40 degrees or even more in some cases. The Oort cloud comets are spherically symmetrically distributed, and typically these are one-time visitors, and they have very long periods. Okay, and among the most recent of detections is the main belt comets. These are asteroids. These are objects in the asteroidal belt, and most of the time they have asteroid-like behavior. But once in a while, you start seeing some coma and tail. So these are recently discovered, and it's a very active area of research with relatively a lot of resources being poured in. Comet naming we can discuss subsequently in case somebody is interested. So I'll just leave this slide here. Now, for those of you who are more interested in looking at pictures and stuff, so I thought I should show you some images and movies. So when I said that comets move around the sun, so there has been this very important mission to the observing the sun continuously, which is called the Solar Heliospheric Observer. So this observatory is located at the L1 point, and it is able to continuously monitor the sun. So, in fact, it is one of the most prolific comet discoverers, especially of sun-grazing comets. Okay, these are comets which come very close to the sun. Most of the time, they are discovered only by the SOHO mission, which has discovered more than 2,500 of them so far. And most of them actually end up in the sun, and they get eaten up by the sun, essentially. But we'll see a few. So this, for example, is the famous comet Hadley, which came in 1996. This was a very fast and very swift comet. And you can see how it moves across the field of view. And just stop the video here for a moment. Yeah. And you can see the broad dust tail and the very thin and narrow gas tail, ion tail. Okay, and how the tails change direction as they move across the field of view. So, in fact, if during the history part, I wanted to also mention that Tycho Brahe was one of the people who realized that that the comets' tails were always pointing away from the sun, which was an interesting observation from ground-based observers prior to telescopic observations. So in this, of course, we see that happening in the same way here also. This is the very famous comet 2011 W3, and this comet, in fact, if you see here, you can see that the tail is still rounding the sun while the nucleus has gone, just a moment, has crossed the sun and come back in the field of view. And in fact, it came so close to the sun, 0.005 AU, that it lost the tail. Okay, it got disconnected from the tail. The tail is still passing here, and then a new tail emerges out at this point, as you will see when it moves across. So there you see the tail developing and going ahead. So this comet, in fact, was discovered by Terry Lovejoy, Australian amateur astronomer, with a very small telescope. And it was one of the first crude sun grazer discoveries from ground after nearly 40 years of observations. Okay, and this discovery happened on 27th November, and the perihelion of the comet was on 6th of December. So extremely fast and rapid movement. And when it actually came back after perihelion, it was possible to see it in spectacular fashion in the southern hemisphere. Okay, and this is a photograph taken by Dan Burbank, astronaut on the International Space Station, and it shows how spectacular the comet looked just rising above the Earth's atmosphere here. Similar photographs you will see if you search for Google Images on this object. You'll see a spectacular sequence of images. There's one by Guillaume Blanchard on the European Southern Observatory, where the VLT is situated, where you can also see the spectacular views of the LMC and SMC and the Milky Way. Okay. Pan-STARRS 2011 L4 was another very majestic comet. And this one, of course, reached naked eye visibility. And in fact, we were also able to see it a couple of times from Mount Abu with the naked eye just after sunset and before moonrise. This showed a very broad fantail kind of distribution in the dust. And a lot of theoretical work has happened in modeling that. And you can see some of the information about this comet by going up to this link on the NASA iPod series. I just show a screenshot of that. It's a small subset of the screen because it's a very long pic. You can have a look at the full screen at this link. And it also shows you explanation for how these striations and features you see in the dust are happening. And this comet, when it moved further as relative to the Earth, and we also moved along in our orbit, we could actually cross the plane of the orbit of the comet, and we could see the very thin and very long tail. In fact, it's called an anti-tail because it's pointing towards the sun, apparently pointing towards the sun. And this view is something spectacular. Some comets have been traced almost to have 90-degree long tails when we cross the orbit of the comet at that time. Coming back to things that we have been able to do from our Mount Abu observatory, this is a view of one of the other Lovejoy comets, C/2013 R1, I believe, which I don't know whether you're able to see or YouTube is stopping you from seeing it, but this is the comet here, and you can see the hint of a tail here in this direction. This is a meteor taken, which just happened to come in the same field of view during the long exposure taken by Rakesh Rao when he was visiting us at the observatory. Dust and other things of the in the Earth's atmosphere, and then just beyond. This is zodiacal light, in fact. So these are all seen in this spectacular image. So what are the things that we can do when we study comets? So some of these results I shall be talking. So these are now slightly technical. So if you have questions on these, we can discuss in more detail. I'll just show you some of the results. Spectroscopy basically means that you are taking a kind of rainbow, if you will, of the comet, and because it's an extended object, you normally place a slit on the across the comet and then record the spectra. Okay, so the spectra are recorded on a two-dimensional detector called a CCD camera, and this is not very different from a digital camera which you see in your mobile, but much more sensitive. Okay, and after doing a lot of processing and removing all the instrumental artifacts and then the continuum and everything, you get a spectrum which looks like this. Okay, it has signatures of a variety of molecules, which are all actually daughter molecules from the in the coma of the comet. Okay, and if the comet is bright enough, you can actually plot spectra all along the coma, so all along this direction or this direction, and then you can see how the molecules are moving across and developing in the field, in the coma. Okay, so this is the comet again. This is Comet Lovejoy's 2014 Q2, I believe. Yeah. So these are different bands we can discuss if people are interested. So these are some of the other comet spectra which we have obtained using the Mount Abu observatory telescopes. We have a 1.2 meter as well as a 50 centimeter telescope operational, and very soon a couple of other telescopes will also be joining in. We have another 43 centimeter telescope there for exoplanet observations, and a 2.5 meter will be coming up soon. So these are some of the other spectra which have been recorded, and you can see that each of them is quite different. In fact, if you look at 2016 R2 Pan-STARRS, this looks quite different from all the other comets. In fact, it was quite depleted in C2, this molecular chain of comet, carbon chain, and this actually CO plus and other features were quite dominant in the 2016 R2 comet. So this was quite different from the Lovejoy and other typical comets that we have seen, and there's a lot of interesting work that has been done with it. There are, when you look at the periodic comets, then in some cases you start seeing that they are quite depleted um, in terms of their um, in terms of gaseous emissions, and they look almost asteroidal in nature. And this is one example, 123P West Hartley. And so just showing you to show that, comets have quite a large variety of spectra. And in some cases, you can see that there's a change during the perihelion pass, and after perihelion, you have more activity. So similar results we were able to get for this interstellar comet. This was a real visitor because you see it did not belong to our solar system. So in fact, how do we know that it was not part of the solar system? Is because it had an hyperbolic orbit with very high velocity, and which meant that it would not be able to escape. It would not be gravitationally bound to the sun, and this implied an interstellar origin. In fact, it's the only second object which has been discovered, and that is how the name 2I, with interstellar characteristics. This particular object is completely cometary in nature, while the previous one was completely asteroidal in nature. And we were able to study this using two Indian telescopes. So most of the results that I'm showing you are from our work. So I'm quite so I apologize that I'm not covering a lot of other research that has been done in this field. It's not going to be a review of the whole field. That's a very big job if I have to review the entire body of work on comets. So I'll just briefly set the stage and then we'll discuss. So this particular comet, we took the spectra using the Himalayan Chandra telescope, which is a 2-meter telescope in Hanle in Ladakh. And the observations are done remotely from Hoskote near Bangalore. It's a telescope operated by the Indian Institute of Astrophysics. And so when we looked at this comet, which was, we were not expecting to be able to see it because most of the work that had been reported in the literature was from 4-meter class telescopes. In fact, some of the results were also from the 8-meter VLT and other telescopes of similar size. And what we found in half an hour's exposure, multiple exposures of half an hour, was that there were the same kind of signatures as seen in solar system comets, except that the signatures were quite low, especially for the carbon chain. The C2 and the C3 were quite low in intensity. So what we concluded was that that this was similar to the carbon depleted comet of the solar system, and this is an important result because it shows that this comet also formed in the protoplanetary system of some other star, and with a similar kind of behavior, similar kind of composition, and a similar kind of evolutionary characteristics as expected in the solar system, which meant that it's not necessary that the solar system's evolution is of a unique nature. Okay. So going ahead, the other technique that we can use is polarimetry. So what do we do by studying this is that we are able to understand the properties of the dust which constitute the coma of the comet. So the coma is visible because of sunlight scattered by the cometary dust. And once you have scattering, there is polarization. And this polarized light allows us to understand the properties of the dust in terms of the composition and the nature of the dust grains. So here, for example, is a polarization phase curve, which constitutes all the observations for Comet Hale-Bopp, which are shown as solid line. Most of these were taken from Mount Abu Observatory during the apparition when Comet Hale-Bopp was bright enough to be seen even by the naked eye for almost 18 months. So these observations, added with the other observations of other comets, show that it had much smaller it was dominated by small dust grains compared to other regular comets. And each of these dots represents one night of observation. And it's the kind of it's pretty demanding to observe comets. Maybe if we have time, we'll discuss it further. So what do we do once we have this kind of phase versus polarization plot is that we compute theoretical models, and then based on scattering calculations, one can compute the dust parameters. So once you do that using supercomputers, because normal computers are too slow for this kind of calculations, then you can come up with models of different compositions and different refractive indices to explain the observed polarization. So here we have three different observations shown in red, green, and blue dots. These are taken at three different wavelengths. And the model shows models were calculated for a range of silicates and carbonaceous materials, and taking a fixed value of the refractive index and considering different types of materials, hierarchical aggregates, meaning that they were dust grains composed of various sizes, and then fluffy solids of 75%. So in that paper, Pritesh and I were able to show that there were several comets which we were able to explain with a varying sequence of compositions and dust morphologies. And these are over a large range of orbital period, which means that our model was able to successfully explain for most of them. Further work is in progress in this aspect, and hopefully we'll see how it develops further. So this is, to conclude, is one of the most spectacular comets of recent times. In fact, if you look at the ASI outreach page, you will see that last year the ASI conducted this campaign and a contest to photograph this comet C/2020 F3 Neowise. And some of the most amazing images and majestic images from the apparition were shared on that link. In fact, 5 of them are still there online, I believe. And this particular one received a special mention from the judges. And Dorje Amchuk's other image, I think, won the first prize, if I'm not wrong. So this particular one shows the comet in just adjacent to the observatory. So it's quite amazing that he did this kind of meticulous planning to be able to predict where the comet would appear, and was in place to get this amazing view. So this particular comet was bright enough, and we were lucky enough to be able to get a spectrum in 3 minutes of exposure. So you can imagine how bright this object must be compared to the interstellar comet and the other comets where we needed more than half an hour of exposure, right? So this also shows very spectacularly the coma and the dust tail and the ion tail and the separation between them, and how very well the photograph has, the CCD camera has traced the very long tail here. We were just able to detect it with a digital camera here in light polluted Ahmedabad, but I think at Hanle, Anchuk was telling me that they were able to actually see it with the naked eye. I believe it would have been surpassed only by the Comet Hale-Bopp of 96, 97, which was just there outside if you went out to see. So I will stop with this and take questions, and I hope we'll have an interesting discussion.
Thanks for the wonderful presentation. So we have some questions, and I will start with a very basic question, okay, which has been asked both on YouTube and Zoom. Okay. So people want to know more about how comets are formed.
Okay, how comets are formed. So this is at the time of formation of the solar system. So the in the protoplanetary disk stage. So these are objects which are settling down. The sun is just being born, and then you have material floating around in a disk around the sun, because the protostar there's a angular momentum which makes the dust and all the gas material to condense into a disk. Okay, so in this disk stage, the objects are being brought together. Okay, and then in fact, if you look at some of the ALMA images in millimeter, you can see this kind of actual formation happening in protoplanetary disks. And where the planets start forming, you will see that there's gaps. So these are seen in the ALMA images. So what I'm talking is actually being discovered even observationally now, although initially it was only theoretical models. But now it's being tested and shown by observations. So what happens is that when these objects are formed, so many of them end up coalescing into planets. Okay, but many of the material gets thrown out because of the giant planets which are formed. And Jupiter and Saturn, for example, were responsible for throwing out a lot of material when they were born. And these materials were thrown out far enough away that they settled into a spherical shell. That's a hypothetical shell around the star. And that is the place where most of them reside. And only when they come in closer to the sun, they start showing their activity and develop a cometary tail. Okay. So I hope I'm able to answer it.
So how do we distinguish between comets and asteroids?
Okay, so that's a more interesting question. I did not want to touch about asteroids, but asteroids are more rocky objects, and they are not thought to be having as much ice as in comets. That is a very simple difference. But then the more important difference is that the asteroids have an orbit which is confined to the belt between Mars and Jupiter. So these objects should have actually coalesced into another planet, but because Jupiter was massive enough, it was able to disrupt that formation, and you ended up with the asteroid belt. But interestingly, as I mentioned, many objects have been detected in the asteroid belt with comet-like emissions, and these are very active areas of research to understand how we are seeing cometary activity from this kind of objects, which are not coming very much closer to the sun than their usual locations.
But we also have these minor bodies which are asteroid-like rocky bodies. We also in similar elliptical orbits, right?
Yes, so yes.
How That's come we have some bodies which show comet-like activities, have this lot of ice, and then they form tails? And then in the same region of the solar system, we also have some bodies which don't have any ice.
Yes. In fact, there are also comets which have been observed to have switched off activity. So these are objects where the upper layers. So these are objects which might be quite heterogeneous in surface, and they have lost all their active surface area, which was usually with ice, and they have become dormant because they no longer have the kind of material which is required for activity to show up. As far as your question regarding the elliptical orbit asteroids, so these are objects which in fact cross the Earth's orbit also sometimes, and these are objects which are termed as potentially hazardous objects, and in fact they have the probability of crossing the Earth's orbit. So these objects have also been observed in terms of whether there is activity in them. But to the best of my knowledge, none of these objects have shown spectra like the way we see in active comets. But they are mostly dominated by rocky material only. Yeah.
So there's a question about a specific slide. You showed a spectra about comet Vitanen.
Okay.
So there was this huge peak at 4,000 angstrom. So
okay, right.
What was the reason for that?
Yeah. So these are there are a lot of cometary peaks emissions which are seen here in Virtanen compared to others. But if you look at this one, you will see that there is a good chance that it is actually C3. There may be other molecules here, and this is still being looked into. But this is C3, then you have the two C2 peaks, and then you have several other, like NH2 plus C3. So these are typical cometary molecular emissions. And you get the same kind of effect here. Now, in terms of this line, which is the oxygen line, we have to be careful because we also get terrestrial oxygen. So that is one thing which we need to keep in mind. Yeah.
So these kind of spectra, can the undergraduate or postgraduate students capture this kind of spectra using the spectrograph which are typically found in the colleges?
Okay, so actually, so if you're able to link that spectrograph to a telescope, then it's a very easy proposition. You only have to point the telescope and then track the telescope on the comet. So this is not something very straightforward to do. But what can be done is to put a grating. So normally, your comet, your telescopes have a filter wheel with a CCD, and this filter wheel has filters which are of different wavebands. So in that place, you can put a grating, and you can also obtain spectra. So many amateur astronomers are doing that kind of work also. In fact, our work here on 2014 Q2 was with a very prominent amateur astronomer in India, Vikrant Agnihotri, who has set up quite a extensive rooftop observatory at his home, and he helped us with the observation. So we were quite happy to have his inputs. So this kind of work can be done, in fact, with telescopes and spectrographs costing very, very less amount. Okay, they're well within the reach of the colleges and universities of India now. In fact, many of them can be built in-house, I believe. Yeah.
So there is a question that can you comment on linkage between interstellar ice and cometary ice? So probably the person means that ice which is on the outer reaches of the solar system and cometary ice, probably.
Okay, that could be one interpretation. The other is that I was mentioning that that the dust which you see in comets has similar spectra as in young stellar objects. So these are objects which are relatively early time of their formation. So they, in fact, if you see their spectra, they look very similar. You have the same kind of amorphous and crystalline silicate signatures between 8 and 30 micron. Multiple signatures are seen, and they have very similar behavior as seen in case of Comet Hale-Bopp for one, and then in fact even for Comet Temple, which had this deep impact mission. So if you look at the spectra before and after deep impact mission, then after the impactor collided with the comet, then you see that there is quite a lot of difference in the way the dust characteristics look. But yeah, I guess I don't know what exactly she means by interstellar ice.
Okay. I think we'll come back to some more questions from YouTube later, but Sarita, why don't you take some questions from Zoom chat?
Hello.
Yeah.
Yes. So yeah, I will take some questions from Zoom, and I have my own questions. I hope we get some time for that. Okay. First, there's a question by Varun, and he wants to know what are the properties. Can you please explain what the properties of the dust and ion tails of a comet?
Okay. So regarding the dust and the ion tail, so the dust is basically the sunlight scattered by the dust material, and to observe that we use the continuum bands. Okay, so between these bands, so these are the bands that we use for observing the dust properties. Okay. And so there's a blue continuum further on the blue side. There's another, that's a UV continuum. Then you have a blue one here, then green, and then a red. So these are the bands that you use for looking at the dust properties. The gas tail and the ion tail you can see using the other narrowband filters. Like these are the.
But why do they form two tails? I mean, they are mixed. They would be mixed, right? Yeah.
So let me just show you one picture and then I'll explain. Yeah. So this one, in fact, is a spectacular picture because here you can see that the gas tail is quite distinctly seen compared to the dust tail, right? So this is because the dust is being ejected from the cometary nucleus, and each of them, because of their mass, they are following in the orbit. So each of them is again sharing the orbit of the original parent comet. And but on the other hand, the gas and the molecules, these are much lighter, so they just follow the solar wind. So because of that, you see this strong distinction between the gas and the dust tail.
And the dust tail would be tilted, right? I mean, slightly curved.
Yes, slightly curved because it's following the orbit of the comet. Okay. In fact, if you look at this picture, in this case, so these are cometary dust which have been released from the comet a few days earlier, and then these are more recent dust. So there are the different ways of modeling them, and it depends upon the view that you have of the comet. Not all comets will give you this kind of a view.
But here one can't see the ion tail, right? I mean, not clearly.
Here one cannot see because this was a very dust-rich comet. And so the ion tail is not visible.
Okay, so that probably explains why some of them are very broad and why some are very narrow, depending on the dust content.
Yes. Yeah, and the color also. Like this one is almost like sunlight, whereas you see many comets of recent times were gas-rich, so they had this bluish green color coming from the sea.
Like the Neowise one, the one you showed some time back.
Yes.
Okay.
Right. So there, in fact, I apologize, I keep shunting between these.
No, that's fine.
So this, for example, this is the coma, which is very rich in the dust, in the, the CN and C3, C2. So these are all blue colors. Okay, so they dominate the coma here. And then the tail is dominated by the dust.
Okay.
And you can see this changing geometry if you recall in the Soho movies that I showed.
Yes.
See the separation changing with time.
Okay. There's a question which is I'll just put across the question as it is. How do we explain Tycho Brahe's observation? I mean, in the context that you mentioned, I don't think anything more is given, but
yeah, nothing more is known. He was a very good observer, that is for sure, because with just his eyes and his instruments, just measuring the different angles between the stars and the planets, he had recorded their positions to sufficient accuracy for Kepler to come up and use the observations to, deduce his laws. So I believe he was a very meticulous observer, and he really did this observations of the cometary tails and then saw that they were pointing always away from the sun. So that's something amazing that he could do this in the era when he did not have access to a telescope. I wonder what he would have done with later years equipments.
Okay, so there's a question by Amrit Mishra who says, who wants to know what additional knowledge would sending spacecraft to collect samples from Comet give?
Okay, that's a very important question, one that I did not touch upon at all in this discussion because I focus mostly on work that we have been doing. So what can be done by visiting comets is that, for example, in the case of the most famous spacecraft which has gone to a comet and observed it in close detail is the Rosetta mission. And this comet, in fact, this spacecraft went through and through the tail and, in fact, flew around the coma of the comet. In fact, it approached the nucleus very closely, and it has some spectacular images of the jets and features coming out from the nucleus of the comet. Comet 67P Churyumov-Gerasimenko. Okay, so it's a spectacular result, and there were, in fact, a suite of instruments on board, ranging from mass spectrometers to imagers to all kinds of things that you can imagine. And imagers of all kinds, spectrographs, and these have been used to tell all kinds of results about the material which are seen in the very inner regions of the coma. Like you can measure the uh, uh, concentrations and the abundances to a very high accuracy, and you can also look at the origin of how the jets and other features are seen in comets, how they start off and go ahead. So these data are all publicly available on the ESA and NASA websites, and those interested should definitely look into using those data and trying further work on that. I would really urge people to look at that in more detail. And yeah, there have been, of course, for Halley, of course, there were many comet missions which were mostly flybys. In the case of Rosetta, it actually orbited actively orbited the nucleus and followed it right through perihelion and beyond. Okay.
Okay. So we go to the next question by Satyapriya, who says that you said that generally the tail goes away from the sun, but I think in one of the case you had shown that the tail goes at 90 or 180 degrees from the general one. I think you mentioned about the anti-tail. So could you elaborate on this?
Okay. I don't know if it's the anti-tail or whether she means the relative angle between the dust and gas tail.
Maybe you can mention both if it's not clear.
Right. So when you, for example, when you look at the Comet Lovejoy, this movie. So here you can see that the cometary tail, this is the gas tail, dust tail, and then the ion tail was here. And then at this point of time, the comet had reappeared on this side, but the tail was still pointing. So when it goes very close to the sun, then you have a lot of material which is still left in the orbit, and then you see that these are quite distorted. It also depends upon our viewing geometry. Like if you are viewing from a different perspective, you might see a quite different view of the comet. Okay, these are mostly two-dimensional objects, and if you see them along the orbit, you will see a very long stretch of dust debris. But if you see it across the orbit, you will see it as a fan shape. That kind of behavior you will start seeing. I don't know if I answered the question completely. Otherwise, we can.
I think that is 90 degrees, right? And what about the anti-tail?
Okay, the anti-tail is because of, again, viewing geometry. It's not exactly that it's a jet or a dust jet pointing towards the sun. Dust jets which emanate from the nucleus pointing towards the sun would quickly bend away and move back towards the tail of the comet.
Okay. So I will move to the next question, and that is by Pradeep, who wants to know that do comets originating from the same belt or neighborhood share characteristic spectra? What are the parameters that might affect the elemental composition besides orbital radii?
Okay, so so if they are belonging to the same family, they tend to have similar spectra. But again, it depends on how much activity is there and how close to the sun they come. Okay, because the perihelion distance might be different, and each apparition is different. For example, in periodic comets, you might see that there is a change from one perihelion approach to another. So the cometary spectrum can be quite different even for the same comet at different times and at different orbital apparitions. Okay. So that's the short answer to that question.
Okay. So what are the parameters that might affect other than orbital radii, affect elemental composition other than orbital radii?
Other than orbital radii, okay. So there, I guess it should be other than orbital radii, the orbital approach to the sun. It would also depend upon what kind of orientation the cometary nucleus is having with relative to the sun. For example, whether the how it is, comets themselves also are spinning. So these objects, whether the spin orbit is spin axis is in the direction pointing towards the sun or away from the sun, what kind of activity is happening. So these are the kind of things, and whether the nucleus surface is homogeneous or heterogeneous. So a lot of differences can happen from comet to comet, and even from within the comet, for the same comet before and after perihelion, you have completely different looking spectra. Yeah.
Okay. So we move to the next question by Amit Mishra, who wants to know what kind of evidence are we seeking from comets to confirm the possibility of life. He's talking about technical evidence because they have ice and some other essential elements. Is it possible to confirm it by observations, such observations?
Right. So in terms of life, it's a very complex question, and I really am not an expert on that. But then what I can tell you is that a lot of complex organic molecules have been detected in comets. For example, the ALMA millimeter observatory has detected a large number of very complex molecules. In fact, even alcohol has been detected in one of the comets. And so you can, in fact, several other even higher organic chain. So these typically the observations that we do at optical band, they are these remnants from the longer carbon chain material, which were seen, which are the parent of the C2 and C3, for example. And it is not completely known that what are these parent molecules. But typically they are these complex organic molecules. As far as confirmation that really life is there on these objects, that is not a very straightforward question, although it's a very long-standing hypothesis that comets brought life to Earth. So whether they brought water to Earth is the first question, more importantly.
So what about amino acids? When you're saying that complex organic molecules have been observed, amino acids, I mean glycol, has that been observed?
Yes, too? Yes, I think some have been seen in a couple of cases. Yes,
I see. Okay. Okay, so can we move to the other question? There is one by Ishan who says the famous 2017 interstellar comet Oumuamua was observed only when it was about to leave our solar system. Correct. If it were observed a little sooner, what all information could have been gained from it?
Okay. Firstly, that was interstellar asteroid, not a comet, the first one, to 2017 object. And it was seen, in fact, only after it was leaving, because it was at that point of time that it became bright enough to be seen because of the relative geometry between us and the sun and the object. Okay, so since it was an asteroid, there's not much that in terms of features that we could see, spectral features. But had we observed it earlier, it's possible that we could have tried longer exposure spectra with larger telescopes to see if something else could be known about it. It's not very easy to find something on an object which doesn't have any spectral signatures other than the continuum from the sun.
Mm-hmm. Okay, so the next question is from Utsav, who wants to know why do comets have highly eccentric orbits?
Okay, so these are in terms of the allowed orbits from those distances, and most of the time they spend their time away from the sun, and due to some orbital perturbations, either by passing nearby objects or other cometary material in that area, they get thrown inward. Okay, and typically interaction with other massive objects in the solar system. For example, Jupiter is responsible for converting many of the long period comets into short period ones. And because the sun is really the most important influencer, it ends up having an elliptical orbit. And between the sun and Jupiter, Jupiter, of course, is the one which is responsible for clearing up most of the mess. Otherwise, the inner regions would be quite left unprotected, essentially.
Okay. So another question is from Rohit, who wants to know how far from Earth can we detect comets, and can we know their temperature and other properties?
Okay, that's a fascinating question. Okay, how far can we actually see this? Okay, so in fact, see this comet Hale-Bopp. I will answer it with some examples. Comet Hale-Bopp was in fact observed in 1995 and all. And in fact, they were able to trace it even beyond Neptune. So almost beyond 30 astronomical unit, in fact, in 2010 with the largest of telescopes available to the astronomers. In fact, now recently I did not have time to cover that there is one comet which is approaching Sun in the perihelion in 2022 December. And this object is showing comet-like activity at extremely distant distances. Okay, it showed comet-like activity at 8 astronomical units. Then it was still quite far away from the Sun. And at that distance, you do not expect any kind of cometary activity. Cometary activity starts appearing only after it has crossed the around 4 to 3 AU, in fact lesser, because you want to sublimate the ice and release the grains and dust and gas at that point. So there is some other mechanism happening to explain the cometary emission from this kind of object, which is at such a far off distance. So these are objects which are being probed with other bands also. For example, there is the proposition that cometary emissions in the UV might give some clue, because optically you do not see much of an evidence for any gases, but then you see a coma in the optical, which means dust has been released. Okay, so
have UV observations been done? I mean, when, for example, Galax was up there, or
right. So they have not been done with Galax, but then we have proposed with AstroSat. Observations were done, but we're waiting for the data now.
I see. Okay. Okay.
There have been observations, of course, with HST and other spacecraft. But
so was that a far UV also? What did they see? I mean,
so no, not really far UV. So near UV, actually in the CO plus and this kind of bands you see in the UV, and this has been seen in a couple of objects, but not at such distances. So those are distances which have not yet been probed.
Okay, there's another question from Zoom. I think this is the last one here. From Rima Ghosh, who wants to know what is the ratio of asteroids to comets in our galaxy. I believe they're talking about numbers.
Okay. Okay, so
probably we should modify it to in our solar system, not necessarily galaxy.
Yeah. I think not galaxy. Let's talk about solar system at least.
Right. Yeah. So in terms of known objects, because one can extrapolate from there to what you would expect. So yeah, I guess it's a much larger number. So asteroids, of course, are known in much larger number than comets, but that's simply because they probably have been seen. But comets, because they spend most of their time farther away and are colder material, so they have not been seen in such large numbers. So actual numbers, I will not commit myself without really looking at it. But comets, we have a few thousands, but asteroids are in much larger number.
Known ones, in terms of known numbers?
Known numbers, yes.
Okay.
Yeah.
Okay.
So, but then I would expect that there are more comets than asteroids.
Okay. Okay, so Aniket, I think the questions are in Zoom. We are over. Are there more questions in YouTube?
Oh, yes, there are some interesting questions which I want to definitely take.
Okay.
So one question is, are binary comets possible?
Binary comets are indeed possible. In fact, what happens is that in some cases, comets split, okay, and then they share orbits, and then they have they are named accordingly. only. And then you normally see that one of them survives and then the other goes away. It depends upon the size of the comet. And they will be sharing the orbits. Sometimes you can see them. So in fact, this interstellar comet also split up after perihelion pass. And so that happened with that. And in fact, the other one which I showed you, the comet which was orbiting Jupiter, it split up into 21 different comets, right? So binary is definitely possible. It's not that it will remain stable for long, because
so
there's relative activity. Yeah.
Another very common question is, it is generally said that the comets are responsible for presence of water on Earth. So why it is said that?
Right. So in fact, if you look at the isotopic abundances and such, then it is said that it is the asteroids which are closer to they have closer isotopic abundances to rather than the comets. So only a couple of comets have been shown to have water with similar isotopic signatures as seen on ocean water. So it's not a settled question yet. It's still open to debate.
Okay. So there are some questions. So somebody asked, are comets, do comets pass very, very close to Earth? But more importantly, there is another question, which is, what if a comet actually enters Earth's atmosphere? What will be the effect?
Right. So, yeah. So in fact, there are a couple of theories where it was not asteroids, but comets which killed the dinosaurs. So it's always a open question, like how do you know what really killed them? But the thing is that if it's a comet which enters the Earth's atmosphere, it would depend also on the mass of the comet, most importantly, because if it's not a very big object, it might just burn up in the Earth's atmosphere, depending on how far it approaches, how closely it approaches. But if it survives the Earth's atmosphere, then it may end up creating trouble quite significantly, because it depends also on where it lands. If it's in the ocean, it will lead to tsunamis of untold proportions. So, yeah. So, in fact, there's a
related question that can something like Tunguska event, which happened in Siberia in 1908, can it be caused by comets?
So that's again a question whether it was a parent object was a comet or an asteroid, and more likely these were asteroidal in nature. It's not very clear, because comets you would end up, I believe, they would break up unless they were really massive. And if they were really massive, then you would see much more devastation than the Tunguska event.
But theoretically speaking, if it is just purely mostly a ball of ice, then while it heats up in the atmosphere, it should simply vaporize and should not cause destruction. So why there is a destruction because of comets?
No, it will depend on the amount of material that is available, right? So, in fact, at the top end, you may end up having some amount of shielding, and it can reach the Earth because see, for example, in some cases, comets have been known to be of several kilometers across, much larger, in fact, almost comparable to some of the more bigger asteroids. So it can be quite dangerous.
So in this regard, I just, sorry to just comment that way. I just had this question. So if you look at the composition of comets, it's not uniform, or is it? In terms of the ice, or it does, when we talk about the nucleus, we say it's rocky, but then there is ice on top. So does it mean that the composition wise it's not very homogeneous, and there is something rocky, and then it's covered with, has ice mantle? Is it like that?
So there is no real differentiation, because these are materials which were just in the beginning stages of the planetary formation. So they are not differentiated material. Okay, they are not massive enough to have a rocky core and or an iron core and a mantle like that. So they are quite heterogeneous mixture.
Then what do we mean by nucleus when you say, like, for example, Rosetta mission went and it said went
so
to the
nucleus
nucleus?
is the bare material, bare object which when it is far enough away from the sun, there is no activity. So that is the object which you call the nucleus.
Call the nucleus. Okay. Yeah. But more or less, it is homogeneous.
No, that part is quite heterogeneous in material. Yeah.
Oh, I see. Okay. Okay. Yeah.
So, okay, one last question from my side. So, in haven't been too many instances of Indians discovering a comet. So, what are the typical challenges in hunting or discovering a comet?
Okay, so in fact, the only one which we know is Professor Bapu, and he did that in Harvard with a photographic plate. So the main challenge is, in fact, you need a lot of dedication. You don't really need very advanced technology. You need to know the sky extremely well. And especially if you are sitting and observing the very early dawn or very late evening, very early evening, especially in the dawn skies. So at that time, if you know the sky very well and you are scanning that area with a binocular, you can definitely discover. So it's not a question of any technical limitation. It's just that people have to do it. For example, Terry Lovejoy, who is on the screen here, he has discovered nearly 6-7 comets, and he doesn't have any real major equipment as such. It's just a small telescope, which almost many people can afford in India now. Like, it's not very expensive, maybe a couple of lakhs at the most. But in fact, people have even discovered comets with the naked eye also, and then with binoculars.
You just need dedication.
Yes, you need to know the sky very, very well. Yeah. That's something which is. So you really need also extremely good skies. So that is something which is another point which needs discussion.
And patience.
Yeah, of course, patience goes without saying. You need that.
So. Would you suggest a book for students to read if they want to do a theoretical study of this subject?
Okay. Theoretical study of this subject. I think best would be to take some of the review articles and then start from there. So there are some articles on then general astronomy textbooks are there, I guess. Cometry textbooks, there are a couple which have been written after the Rosetta mission, so those could be of interest. Not specifically able to list something out of.
I think introductory textbooks, astronomy textbooks which deal with Comet.
Yeah, they would deal with it. There is another nice book on planetary science.
Planetary sciences, that's right.
Yeah. So that's the name of the book itself, Planetary Science.
And the author is with Lisa, I don't know.
Yeah.
Lisa with something with L. Let me locate it.
Yeah. I don't know if Arvind is there. He can type the detail in the text. Let me just check.
Okay. I think... okay, there is one more question. Can we predict accurate value or accurate lifetime of comets? That once we see some comet, can we say that how long the comet will last?
Oh, okay. So typically, life for a comet. In terms of activity, we call it a dead comet once either it has disintegrated or there is no more activity because the active layers have decreased. Okay, so I'm not exactly sure how to define life of a comet. It's an interesting question. Yeah, because the short period ones would end up dying quicker than the long period ones simply because they have closer to perihelion passes. So, but then again, they would have spent some time far away. So not sure exactly how you would define life for a comet.
Okay. I think, Savita, you can close
Yeah,
this.
we can.
Yeah.
That book, Shashikiran, that book I think is Imke de Pater and Lesueur. Just
Yes,
check.
yes, correct. Yeah,
Planetary Science.
exactly. That's the book.
Yeah. Okay, so we will close today's session, and we thank Dr. Shashikiran for the wonderful talk and illuminating discussion about comets. He gave a historical perspective on these majestic visitors to the inner solar system and also provided an overview of our current understanding of comets through observations and how we can understand their properties. On behalf of ASI POEC, we thank our participants in Zoom and our YouTube viewers for actively taking part in the discussion. We will be back again next month with a new topic of discussion, so do join in. Thank you.